Okay, now we're going to do hyperbola. So the equation of a hyperbola is xy equals a. I should say this is only a rectangular hyperbola, which is the one that we're interested in. There are other types of hyperbola, but this is a special case. It's called a rectangular hyperbola, but it's the one that's most sort of simple. All right, xy equals a, or if we divide through by x, we would get this one here, y equals a over x. Okay. Just want to remind you that a hyperbola, the rectangular hyperbola, looks something like this. I'll just draw one quadrant of it. All right, it would be curved like this. This would be just a generic one, right? And we have to remember that we have these values where it doesn't approach these two lines, and they're called the asymptotes. All right, those are the values that the curve gets very, very close to, but it doesn't touch them. Okay, the asymptotes. So we need to be familiar with that. And that's important. We need those to be able to sketch these. So if it's written like this, then our asymptotes, yeah, I've got that written down here, occur at x equals 0 and y equals 0. Let me explain why. So it's easiest if we look at this form. Since y is equal to a over x, then I cannot put in x equals 0. Because if I put in x equals 0, then I'm essentially saying that y is equal to a divided by 0, which clearly we cannot do that. We can't divide by 0, right? That's how you break things in mathematics. So x cannot be 0 for that reason. Whatever value would make the denominator 0, all right, that's our x asymptote. So in this case here, we can't have x equals to 0. Not possible. Okay. The other thing is why y is can't be equal to 0. And that's because since x is on the bottom of a fraction, then there's no value of x that I can put in here that would make y equal to 0. So let's imagine that we put in very large values of x. If I make this x here huge, like 3 million, then I'd have a divided by 3 million, which is clearly going to be a tiny number. And what if I made it 3 billion? That would be an even smaller number. Well, what if I made it, 300 million or something, 300 billion or something like that? It's just going to get smaller and smaller. But there is no value of x big enough that I can put in that will make y 0. Okay, so y will be approaching 0 as x approaches an infinite value, but it won't ever be equal to it. So that's why we say that y can't be equal to 0. We can't find a value of x big enough to make y 0. So there, that's it. The same thing does apply in reverse as well, I should say. As we put really, really tiny values of x in there, y blows up to infinity. So as y gets very close to 0, as x gets very close to 0, but remember x cannot be equal to 0, but as it gets very close to 0, y will approach infinity, very, very large values. All right, and the other thing that's useful to note is the vertex. So of our hyperbola, I'll draw one again. The vertex is the point where we have maximum curvature. All right, when we do calculus, you'll see that that's where the curvature of the hyperbola is maximum. So we can work that out using the derivative, but for us, we just imagine that it's the center. We can just think of it as the center at the time being. When we do calculus, we can solve for it a different way. But it's always this point here, and the one down here is going to be this point here where the curve is maximized. Okay, so that's going to be at the square root a and minus square root a minus square root a. That's just good to know. All right, with a hyperbola, technically we only need a single point, all right, for a unique hyperbola. But the best practice is when we're plotting these is to plot a couple of points rather than just one and draw it, because drawing freehand isn't very accurate. But I reckon that you should just plot the vertex unless there is an x-intercept or a y-intercept. Then you should plot those, because those are quite easy to find, and also they're kind of important points as well. All right, so let's have a go at sketching one. So here is y equals 4 over x. So this one's quite simple. So let's find our asymptotes first. So what value of x can we not put in? Well, clearly we cannot have x equals 0, because if x was 0, our denominator is 0, which is bad. So that's our first asymptote, and the other one will be y equals 0. Okay, it's going to be y equals 0 because x is on the bottom of the fraction, so there's nothing we can put in for x that will make anything other than there's no value of x we can put in the bottom of the fraction that will make y equal to 0. It will just get close to it. Okay, next we have the vertices, so let's find those. So normally it would be at, like I said, square root a, square root a. So a is 2, so square root a is square root 4, which is 2. So it's going to be a plus 2, or minus square root a minus square root a would be minus 2, minus 2. Okay, so that's because the top is 4, so this is square root 4, which is 2 and 2, minus 2 and minus 2. So let's put those in, plot both of them. Okay, like I said, we only technically need 1 point for a unique hyperbola, but just to help us draw it, let's find a couple more. We can leverage some symmetry here, so let's just substitute x equals 1 in and find what point y would be when x equals 1, because that's easy. When x equals 1, so we'll have y equals, it will be 4 over 1, which is 4. So when x is 1, y is 4. So I will plot that point. Now I'll show you how we can get symmetry. If you draw a vertical line between the two vertices, if you draw a diagonal line between the two vertices, like this, that will be the plane of symmetry for a hyperbola. And in fact, this is true of any hyperbola, any at all. Right? If you draw a line through the vertices, then you will have a plane of symmetry. So we can just use the fact, just pretend it's kind of like a mirror plane, and we can plot this point over here just by the symmetry across those 2 points. So since this one's at 1, 4, then this one will be at 4, 1. We just swap the values around. And likewise, this one here, that's going to be symmetric across in the 2 quadrants. Each quadrant will be the same. So if it's at 1, 4, it should be at minus 1, minus 4. That will be another plane of symmetry. But if you want to check that, just if you substitute x equals minus 1 in, then we get, then if we put x equals minus 1, we get y equals 4 over minus 1. So that gives us minus 4. So minus 1, minus 4. So chuck that in. And then same deal, that means it must be the same at minus 4 and minus 1. Those are our symmetry operators that we can do just to get some other points quite quickly. Because these are rectangular hyperbolas, it makes it very simple. Alright, so let's sketch it. We just join the dots, something like this. Okay, not very good, but there you go. Next one, y equals 3 over x minus 2. Okay, the first asymptote we'll do is x. Now we need to note what value of x can we not put into the denominator. What value of x would make it 0? So what we're saying is that we can't have x minus 2 equal to 0. So that means that x cannot be equal to 2. Right? That's our first asymptote. So that means our asymptote has moved from 0. We've actually shifted it up to 2, positive 2. Like this. So that's our asymptote. So x cannot be equal to 2. So I just want you to note we've got x minus 2 in here, but by substituting x for x minus 2, we've actually shifted the curve in the positive direction. All right, because the value of x we can't have is plus 2. That's an important thing to remember, because when I talk about how to shift curves around, which will be soon, then we need to remember that. Substituting x minus 2 for x means that we shift it up by positive 2. Okay, and the other asymptote is still going to be y equals 0. There's no value of x I can put in there that will make y 0. We can just make it close to 0 by putting big values of x in. Right, and the vertices. Okay, the vertices will be at square root 3, except it would be at square root 3, except we've actually shifted our curve by positive 2 in the x direction, right? Because our asymptote is no longer at 0, it's at 2. So that means we've actually got to add 2 to our x value of our vertex here. Okay, we're shifting it up by 2, so we've got to increase all of the values of x values by 2. But in the y direction, we haven't shifted it at all. It's still at 0, so we can just leave that at square root 3. All right, this is approximately, I'll just point out, the square root of 3 is approximately about 1.7. So this is approximately, so let's see, 1.7 plus 2, 3.7-ish, 1.7. Right, that's not exact, those are approximately equal to. All right, and the other one would be at minus square root 3 minus square root 3. Okay, so minus square root 3. However, we've added 2 to the x value. We've shifted it up by 2, but we haven't done that in the y direction, so minus square root 3 is still there. So this one is approximately, okay, minus 1.7 plus 2. Let's see, that would be 0.3. Okay, and minus 1.7. Okay, so let's plot those vertices. Okay, so approximately 3.7 and 1.7, so 3.7 and 1.7, about there. And 0.3 minus 1.7 is about there. Okay, that looks about correct, so that's good. Next, we're going to get a y-intercept. This one will have a y-intercept. It will not have an x-intercept because our x-axis is the asymptote, but there will be a y-intercept. So let me just delete some things and we can work that out. Okay. So we've done the vertices. All right, so the y-intercept. Now the y-intercept occurs when x equals 0. Okay, remember this time x equals 0 is an okay value to have. It's x equals 2 that we can't have. So that's going to be y equals 3 over minus 2, which is minus 1.5. So that point there. And just because we can, let's just put in another value. Put in x equals 1. Let's sub that in. So y equals 3 over 1 minus 2, which is minus 3. So minus 1, we got minus 3. Okay, and using the symmetry, if we go back by 1, we've gone down to minus 3. So if we go from the asymptote up by 1, we should go up to plus 3. All right, so just using that as that, symmetry there like that. So likewise, we could put this one here, but anyway, let's not. We can use symmetry there and there as well. But anyway, not a big deal. You only need, like I said, just the vertices and the intercepts. Right, and now we can sketch. Okay, there we go. All right, the last one is if it shifts the y-intercept, the y-asymptote, and the x one. So I'm going to rewrite this equation like this. Y equals, now I'm going to add 1 to both sides to get rid of that minus 1. So if I add 1, then I've got x plus 2, 1 over x plus 2, and then plus 1. Now the reason that this is useful is it helps us to understand straight away that if I add 1, all I've done is I've taken the standard curve, y equals 1 over x plus 2, and then I've raised everything up in the y direction by 1. So that means my asymptote, which used to be at y equals 0, right? Y equals 0 is what the asymptote would be, but I've added 1. I've lifted it up by 1. So my asymptote will now be at 1 because I've gone from 0 up to 1. And my x asymptote clearly is minus 2. We cannot put minus 2 in the bottom of that fraction because then I'll have minus 2 plus 2 and that's equal to 0. So let's draw these asymptotes. So the x1 is at minus 2. So like this, and the y1 is at 1. Okay, that's along here like this. All right, now we find the vertices. Okay, so if there wasn't this plus 1 here, the vertices would just be, and there wasn't that plus 2, if we didn't have that and it was just y equals 1 over x, then it would be at 1, 1 and minus 1, minus 1. So they were at 1 and 1. But this time we've got to shift it by negative 2. Okay, we've got to shift it by negative 2 in the x direction because of this negative 2 asymptote. And we're going to shift it up by 1 in the y direction because of this asymptote. In other words, because we've moved our asymptote left by 2 in the x direction, we have to move our vertice left by 2. And because we've raised it up by 1, then we need to move the vertices up by 1. Right, so our new values are going to be -1 and 2. That's one vertex. So let's do that, -1 and 2, right there. And then the other one, it used to be at -1, -1. So now it's going to be at -1, -3, and -1 plus 1. -1, -2, sorry, and -1 plus 1. So -3 and 0. So -3, 0. That's the other vertex. Okay, because this one is on the x-axis, it is the x-intercept, but we don't have a y-intercept. So the y-intercept will be when x equals 0, which will be y equals 1 over 2 plus 1, which is 1.5. Okay, 1.5 right there. Okay, and we can just sketch the curve like this. All right, inside our asymptotes, getting close, but not ever touching them. Oh, that one's not very good, but there we go. Oh, so bad. Anyway, hopefully you get the picture. Okay, so that's the hyperbola.